Hello everyone. I hope you are able to see my screen. So I am Saksham Jain and my team member Gaurav Ambarkar. We are here to present a research paper on virtualized congestion control. Our authors include Madhusudan Ravi, Radcliffe, Alan Bergman, among others. So let's start our presentation. Let's start with introduction. The presentation revolves around the concept of virtualized congestion control. That is, by making the implementation of congestion control of a multi-tenant data center in a virtualized mode, so that physical failures and drawbacks can be taken care of, and the efficiency and utilization of congestion control can be increased. The paper dives deep into the concept of hypervisor translation techniques to achieve arithmetic virtualization for virtualized congestion control. The idea is to use a shared algorithm while deceiving each guest VM into thinking that it is still utilizing its own algorithm. So, the authors have offered an algorithmic virtualization of congestion control in this setup. Each guest is still able to use their own proprietary legacy congestion control algorithm, but the hypervisor implements a shared best of breed congestion management algorithm. Well, what is the main problem addressed in this paper? So the problem discussed here is about multi-tenant data centers, where numerous tenants lease and use a common physical infrastructure to operate their virtual machine workloads. Individual VMs put their own congestion control strategies into practice. However, However, the owner of multi-tenant data center needs to make sure that every algorithm continues to function properly within the shared data center network. Considering this intricate interactions between various congestion control strategies, we need to overcome this problem of different congestion control algorithms and different techniques. The problem can also be stated as that let's imagine a situation where a legacy application runs on the legacy guest VM operating system that uses an old TCP version. This application would have been functioning correctly for years with little to no maintenance needed. But when it has been recently been moved to the cloud and other VMs are using more modern congestion control algorithms, they can starve the older application's traffic. And this is a major drawback. Here, it would be impractical to import the old application to a newer OS and not an option to force new applications to outdated congestion control. Hence, we need to virtualize our congestion control algorithms, which is basically what has been addressed in our paper. So, what's the motivation behind it? The first is fairness in mixed ECN environments. With the current techniques in a multi-tenant data center, non-ECN flows can be starved by majority of the ECN flows because switch buffer can get congested. And the second is dynamic hypervisor based TCP bandwidth sharing. These two will form the basis of our implementation. Dynamic hypervisor based TCP bandwidth sharing is about preferential treatment to a certain application without queuing or dropping packets in the network. VCC layer is capable of dynamically throttling traffic using the TCP to receive uh, TCP receive window. Well, for a short, we have used virtual congestion control as VCC, and these two will be the basis of our implementation later on. As you can see, when we have hardware based congestion control, the performance is not as good and the flexibility is definitely not good because each guest VM uses a different congestion control algorithm as well as technique. When we have full virtualization, we may have a very good flexibility because here the hypervisor will implement a best of breed congestion control algorithm, overlaying all the individual algorithms. But here, as we get flexibility, we may not be able to get performance depending on the situation and all the time. So here, the solution proposed is para-virtualization, that is partial or half virtualization only when needed. Here, the hypervisor will implement best of the breed congestion control, but only between the algorithms that are not flexible with each other, and not every time. Hence, this is the third image is basically how we are going to implement. Let's move on to the motivations. Well, one of the major motivations is also because of the cons of the existing technology. Why we need this new technique? So first is the write into guest memory. In this case, a hypervisor could directly modify the congestion control algorithm, where tenants demand stricter VM isolation, rejecting hypervisor writes to VM memory, even for performance enhancement. When both hypervisor and guest VM control networking stack, memory writes can slow VM due to consistency and synchronization needs. Hence, we will not have as much as performance as we need. Second is read from guest memory. Here the hypervisor only monitors the memory and does not need synchronizations. It could provide access to congestion window without the need to maintain state to track it in a hypervisor. Tenants reject hypervisor access to VMs and using the hypervisor to access guest memory instead of maintaining an internal state machine introduces processing and communication delay. Hence, here in the read from guest memory, we have delays, network delays, and in the write into guest memory, we have performance issues. Let's move on to the other cons of the existing technology. The throttling the receive window. The hypervisor can decrease the receive window to force the guest to have fewer outstanding packets, reducing the receive window to a fewer than the current number of in-flight packets. That could conflict with typical TCP buffer management implementation. Then the other one is split connection. The split connection method involves dividing a TCP connection into multiple sub connections, such as through a TCP proxy. This allows acknowledgement of packets to guest VM at specified rate. This solution demands significant resources for packet buffering, contradicting TCP end-to-end semantics. For instance, an application relying on barriers may incorrectly assume all the packets were acknowledged and proceed to the next phase, hence risking errors due to packets not being received. Then third is the buffer packets. Hypervisor translation layer can buffer in flight packets. That is to be able to resend them without informing the guest. The hypervisor must handle packet buffer management, typically using packet buffers to store rapidly incoming packets, which can heighten latency. Moreover, large buffers notably expand the VCC memory footprint. Let's see our main idea. The main idea discussed in the research paper is about an experiment which analyzes the fairness between ECN, explicit congestion notification, and non-ECN workflows with varying number of each type. It involves 10 senders connected to a single receiver through a switch, with the receiver being a native Linux guest without VCC, acting as a non-ECN receiver for ECN flows and an ECN receiver for ECN and virtual ECN flows. Then all the links have a bandwidth of 10 Mbps and a delay of 0.25 ms, resulting in an RTT of 1 millisecond with a switch queue using RED with parameter set as RED1. TCP new Reno is used as congestion control algorithm for all these experiments, and goodput of long-lived TCP flow is measured using iBuf as a traffic source and tshock for the packet capture and statics. The results demonstrate that the unfairness between ECN and non-ECN flows, where ECN flows share the bottleneck link fairly among themselves, while non-ECN flows experiment significant starvation, especially as the ratio of ECN flows to non-ECN flows increases. Hence, you can see that as we increase the ratio of ECN flows to non-ECN flows, the non performance of non-ECN flows experiences a significant starvation. This highlights the increasing adoption of ECN by application leads to growing starvation of non-ECN legacy applications, highlighting a curse of legacy. Hence, as we increase the adoption of ECN, the growing starvation of non-ECN legacy applications leads and increases, highlighting a curse of legacy. Addressing this unfairness may require alternative switch marking schemes, favoring legacy applications, but ensuring fairness with legacy applications poses significant challenges. In this graph, as you can see, that when we have 9 non-ECN versus 1 ECN flow, it is the good put is basically um, we can see that good put is fair and balanced when we have 5 non-ECN versus 5 ECN flows. The uh, balance hinges towards non-ECN and ECN, and when we have only one non-ECN versus 9 ECN, there is highly unfairness and high bias in this good put graph that we see between non-ECN and ECN. We can see that how the bandwidth has been given mostly to the ECN flows and not to the non-ECN flows, highlighting the non unfairness and biasness. What is the proposed solution that we discuss here? The proposal is to use the VCC translation layer to provide ECN capabilities to non-ECN flows by transforming them into virtual ECN flows. Implementation involves configuring one sender to send traffic through a switch to a receiver, utilizing virtual ECN provided by VCC translation layer. The sender to switch link has a bandwidth of 12 Mbps, while switch to receiver link has a bandwidth of 10 Mbps with a delay of 250 microseconds for each link, resulting in an RTT of 1 millisecond. The system stabilizes for 5 seconds before the data collection of 12 seconds. The observation we get here is of the send window for the VCC experiment, showing a sawtooth pattern similar to the congestion window, demonstrating the creation of virtual ECN flows through receive window throttling. The VCC enables the transformation of non-ECN flow into a virtual ECN flow, which is the proposed solution. The comparison of good put between 9 ECN flows and one non-ECN flow on a 10 Mbps bottleneck link highlights significant unfairness for the non-ECN flow, as we saw earlier in the image 2 slides before. Substituting the non-ECN flow with a virtual ECN results in a comparable good put to a ECN capable peers, with the virtual ECN flow achieving 0.3.8% of the average good put of ECN capable flows. This achievement demonstrates how virtual ECN effectively addresses the unfairness experienced by non-ECN flows. The receive window throttling within the translation layer enables non-ECN guests to emulate ECN peers, enhancing their own good put and also improving the network fairness. Which results that the use of virtual ECN effectively demonstrates the benefit of ECN, particularly in reducing retransmissions. Once virtual ECN is enabled, the lost capacity is recovered because virtual ECN can respond to congestion without resorting to packet drops and subsequent retransmission. The VCC translation layer, by enabling virtual ECN, significantly migrates the unfairness in network performance between ECN and non-ECN flows. This adoption of virtual ECN showcases the virtual congestion controls systems capability in the enhancing of network fairness and performance, offering a solution for addressing disparities among flow types. Now, implementation. Let's discuss the implementation of our proposed system solution. Architectural complexity. In the VCC implementation, this architecture can be utilized to alter packets. With only 37 bits stored per flow, there is a space for more intricate implementation within a specified per connection footprint budget. The primary CPU workload involves maintaining the per connection states of guest congestion control algorithm, hypervisor delay and bypass. Well, the processing delays in the hypervisor can increase the latency. This effect would be more pronounced when the workload of a hypervisor CPU is sufficiently high to cause context switches. High performance virtualized workloads can benefit from bypassing uh, the hypervisor. Um, sorry. Yeah. So this effect would be more pronounced when the load of hypervisor CPU is sufficiently high to cause context switches. High performance virtualized workloads can benefit from bypassing the hypervisor and directly accessing the network interface card using technologies such as SR-IOV. The next is TSO and LRO, TCP segmentation offload and large resource offload. Methods for enhancing the throughput of high bandwidth network connections by minimizing CPU workload. The TSO involves transferring sizable packet buffers to the NIC card for fragmentation, while the LRO performs the opposite task. Hence, the hypervisor must adjust the VCC translation layer accordingly to increase the performance by the implementation of TCP, TSO, and LRO. The next is configuration. Within the VCC framework, the network administrator has the capability to allocate distinct congestion control methods to various ports, IP addresses, applications, and operating system or tenants. The third is encryption. The VCC architecture can also provide encryption services like TCP, crypt, and IPsec to non-encrypted TCP flows. If the guest already encrypts communication, the VCC would require access to session keys and potentially by reading guest memory. And then the last is inside connections. When two guest VMs communicate within the same hypervisor, they still utilize the hypervisor and consecutively pass through the same translation layer. Hence, the VCC is anticipated to function seamlessly without requiring modifications. The other implementations include congestion control delay based. Congestion control, which is delay based. VCC has the capability to interpret delay-centric TCP algorithms like TCP Vegas and Timely by employing advanced techniques like split connections and buffers. This allows for translation between these algorithms with more resource-intensive processes. UDP. As we anticipate that most of the communication would be through TCP, still we need to anticipate we know that most of the communication happens through TCP, but still we need to anticipate UDP communication. Hence, the hypervisor allows UDP traffic to pass through the translation layer seamlessly. Additionally, we could extend this translation concept to UDP, whereby the translation layer converts UDP to custom reliable UDP algorithm, albeit with added buffering and complexity. Debugging. The standardization of all congestion control algorithms to a common reference algorithm, facilitated by the virtualized congestion control algorithm, can significantly simplify in-network debugging. Instead of numerous versions of different congestion control algorithms, there is now a single version of one algorithm. Now, my friend Gaurav Ambarkar will start with evaluation. Hello, Gaurav.
Yeah. Can you make me the presenter, please?
Yes, bro. Okay, Gaurav, you are now the presenter.
So are you able to see my screen?
Yes, Gaurav, I am able to see your screen. Please continue.
So hi everyone, I'm Gaurav. So today I'm gonna discuss about this ECN evaluation. So we implement VCC in two distinct environments. The first implementation is realized at the edge of the Linux kernel TCP implementation. We demonstrate that VCC can help address unfairness between ECN and non-ECN traffic in the Linux environment. And the second environment is a proof of concept system in the VMware ES6 hyperswitch. So first we run an experiment to analyze the unfairness between ECN and non-ECN flows for various numbers of ECN and non-ECN flows. This figure demonstrates the unfairness between ECN and non-ECN flows by plotting the time series of their goodput. It shows that while the ECN flows fairly share the bottleneck link among themselves, the non-ECN flows can become significantly starved. And we can see the unfairness over here. The unfairness grows as ECN becomes more widespread as the ratio of ECN flows to non-ECN flows increases. This unfairness points out of a curse of legacy. As applications increasingly adopt ECN, the holdout legacy applications become increasingly starved. So the next implementation we're gonna see is receive window throttling. So for this unfairness problem, we propose using the VCC translation layer to provide ECN capabilities to the non-ECN flows. Yeah, the figure illustrates the send window for the VCC experiment monitored using the TCP probe kernel module. The observed pattern, which is similar to a sawtooth pattern typically associated with the congestion window in TCP. In the Linux implementation, when the receive window became the limiting factor, the congestion window remained larger than the receive window through the experiment. This rendered the congestion window essentially meaningless as it does not have the impact of the flow of the traffic. So consequently, modulating the receive window directly affect the send window of the guest, resulting the traffic flows that closely resembled those seen with the traditional ECN. This effectively created a virtual ECN flow, demonstrating the ability of VCC to mimic ECN behavior and influence traffic flows in a similar manner. So herein as an experiment with the 10 identical senders connected to 10 Mbps links to a single receiver through a switch is conducted to demonstrate the benefits of virtual ECN in reducing transmissions. So the figure A shows that when the using only the non-ECN flows, approximately 2.3% of the link capacity is wasted on retransmissions caused by the packet drops in the congested queue at the port connecting to the switch to the receiver. However, upon activating virtual ECN, uh, a depicted as depicted over here, the lost capacity is recovered with the virtual reacts to congestion without dropping the packets. This eliminating the needs of retransmissions, so it behaves traditional to the ECN as uh, shown in the picture B. This result this result highlights the effectiveness of virtual ECN in mitigating retransmissions and optimizing network capacity utilization, ultimately improving overall network performance and efficiency. So, restoring fairness with virtual ECN. So the VCC offers ability to transform a non-ECN flow into a virtual ECN flow. So the figure A plots the good put achieved with 9 ECN flows and one non-ECN flow sharing a 10 Mbps bottleneck link. It shows again how the non-ECN flow suffers from strong unfairness And the picture B shows the good put achieved in the same setting, except that the non-ECN flow has been replaced with the virtual ECN. The result good put of the flow from the ECN is now similar to that of the ECN capable peers with good put 103.8%, which we got in the proposed solution of the average good put of the ECN capable flows. So the translation layer uses receive window throttling to cause the guest that does not support ECN to mimic it ECN peers, significantly improving its own good put and the fairness of the network. Now coming to the hypervisor bandwidth sharing, uh, it refers to the allocation and management of network bandwidth resource by a hypervisor in a virtualized environment. So it enables a fine-grained control bandwidth allocation at the application level, addressing the diverse needs of different virtual machines and the applications within a data center. This allows the optimized performance and adherence to SLA targets. So by controlling the end-to-end number of in-flight packets and dynamically adjusting bandwidth limits, VCC facilitates data center-wide coordination of bandwidth allocation. So the figure illustrates a time series of this experiment. It shows that after the introduction of the preferred flows, the throughput of unpreferred flows drops due to receive window throttling, thus providing these preferred flows a larger share of the bandwidth. The total throughput before and after the induction of preferred flows remain relatively constant. So coming through the paper, so the paper written by the authors, they have demonstrated their work in a few ways. They provided theoretical analysis with good proofs to exactly emulate ECN and DCT-CP congestion control algorithms. They implemented proof of concept in the VMware ES6 hypervisor switch. So they provided some theoretical analysis as well as prototype implementations in two environments, Linux and ES6. They demonstrated the effectiveness of the solution more than once through different experiments in these two environments. Uh, so I believe the author achieved the goals they set out in the introduction. So they made it easy to deploy new congestion control algorithms in multi-tenant data centers without worrying about compatibility. Uh, the allow legacy applications in VMs to enjoy the benefits of newer congestion control algorithms. So these are demonstrated via theoretical analysis showing VCC can emulate ECN and DCTCP given a non-ECN TCP guest, Linux experiments and ES6 experiments. So they discussed in detail various techniques the hypervisor translation layer could employ, trade-offs between complexity and benefits, architectural considerations and all. So through theory and practical experiments in the environments, we got the analysis of techniques and architectural discussion. And I believe the paper is well organized and clearly presented. The introduction motivates the problem of deploying new congestion control algorithms in multi-tenant data centers. So there is a logical flow starting from the problem introduction and goals to the techniques to practical demonstrations and deployment considerations to related work and conclusion. So the explanation are clear without dense mathematical details. Figures and diagrams are also understanding. So in this paper, we learned about the legacy congestion control algorithms can start and suffer from unfairness. The translation layer in the hypervisor provides an effective way to deploy new congestion control. The translation layer has multiple techniques like modifying handshake, throttling receive window, etc. So it taught us both the benefits of overall approach, how it can be implemented, and the research challenges that still need to be addressed. But it makes a compelling case for this approach, helping deploy new congestion control algorithms when legacy compatibility is an issue. So in conclusion, the paper introduces VCC, a solution designed to facilitate the deployment of new congestion control algorithms in multi-tenant data centers while ensuring TCP friendliness with non-participating virtual machines. So the VCC operates within the hypervisor layer, allowing data center owners to implement new congestion control algorithms without disrupting legacy applications. And the key features of VCC include internal translation mechanisms with the hypervisors, which bridge the gap between new and legacy congestion control algorithms. The paper also demonstrates the effectiveness of VCC using ECN traffic as an example and highlights its potential impact on fairness among tenants with the data center. Furthermore, the paper outlines a long-term vision for VCC, envisioning a hypervisor translation layer that provides hooks to simplify the coding of new congestion control algorithms. And overall, the VCC presents a promising approach enhancing network performance and fairness in multi-tenant data centers, offering a scalable solution for deploying and managing congestion control algorithms while maintaining compatibility with the legacy systems. Thank you.
Thank you, Gaurav. As our presentation has ended, I, Saksham Jain, and my teammate Gaurav Mumbarkar, thank you all for your time.
Yeah, thank
Thank
you.
you. Thank
Thank
you.
you. Have a good day.